Hello, good morning everyone. I am Dr. Pradeep Sharma, the General Secretary of Biofootprints. I welcome you all here for this wonderful lecture. And first, let me introduce our society. Biofootprint is a not for profit society and it has three main objectives. The first one is to promote science in the society in a very simplistic manner. And the second one is fostering the collaboration between the clinical and the basic researchers. And the other very important objective is to do some philanthropic activities like we do donate stationery items, food, blanket to the kids in the slums. And now I request Professor Sonika Bhatnagar to please come and welcome our today's speaker with a bouquet of flowers. Thank you, ma'am. Now I request our president, Professor Sujata Sharma, to kindly introduce our speaker.
Thank you, Pradeep. How does one introduce Professor Anurag Agrawal? He's got such an interesting profile professionally. Personally, I will elaborate later on. Let me first get started with his professional profile. I do feel that such a person does not exist in our country because our country is full of traditional mindset even when it comes to the profession. So people take up paths and they keep walking on it. They seldom think of changing it or moving into more interesting dimensions or just widening their horizons. And I won't say he's one of those people. He is the only person that I know who's done this. So let me first give you the formal profile. Professor Anurag Agrawal is the Dean of the Biosciences and Health Research, Trivedi School of Biosciences at the Ashoka University. And he is the former director of Institute of Genomics and Integrative Biology, what we normally refer to as IIGB. After completing his graduate medical education at this very institute, that is AIMS New Delhi, he further trained in internal medicine, pulmonary disease, and critical care at the Baylor College of Medicine, USA, followed by a PhD in physiology from Delhi University. Now, you would agree how interesting this profile is. His primary research is in respiratory biology, and broader interests are a new vision of health and healthcare seen through the lenses of emerging technologies. He serves on numerous national and global advisory groups. He has recently chaired the World Health Organization, that is WHO, Technical Advisory Group for SARS CoV2 viral evolution, the Lancet-Financial Times Commission for Governing Digital Health Futures, and he has served on the Pandemic Preparedness subgroup at the Global Partnership for Artificial Intelligence. He has received the Shanti Swaroop Bhatnagar Prize in 2014, the Sun Pharma Foundation Award in 2020, amongst many other awards. And he's a fellow of Indian National Science and Medical Academies. I've always admired Professor Anurag for the way he has not let anything limit his curiosity, his vision. He's just taken his own very path-breaking decisions in deciding his career, and that is why I do feel, is like a guiding light for youngsters and even for senior people like me. And personally, I would say a wonderful person. Like the Jackson song. I've always been like, "Are you there? Will you be there?" And he's been like, "I will be there." Whether it's when we formed the society by footprints, we were literally on our own. Me, Pradeep began, and then slowly we got wonderful people to join us, Sonika, Naval, Enam, amongst other people. And we were literally a fledgling society, and I think now we're slowly finding our feet. He was, I think, one of the first people I wrote to because we were not finding support, honestly speaking, for reasons I won't go into. and I asked him, would you be a scientific advisor for this kind of a society? Fully expecting that I will get no reply, or I would get a reply full of questions, which I was getting mostly. What is the society about? What is the vision? What are you going to do? Blah blah blah. So I was like bracing myself, and I got a positive reply immediately. Yes, of course. That's the kind of person he is, ever smiling and always welcoming, always positive. I don't know how he does it. Something I must learn from you, Anurag. And okay, I think I'm speaking quite a lot now. So without wasting any more time, I invite you, and we are so honored, so happy to have you here today with us. I invite you to ignite our minds with your ideas. Thank
Thank
you.
you, brother. Very, very kind. So it's a pleasure to be here. And you all know Sujata can go overboard in praise. So that's what still very nice to hear. I think one of the key messages for today's talk comes from this. You have to recognize that we are in the middle of change. You have to embrace it and you have to see where it takes everybody. And if you're thinking about it that way, you realize it's actually not that difficult. But you just have to be a little bit more worried about what are the consequences of decisions that you make in second order thinking. The consequences of the consequences, and that really helps. So this is a picture of okay. So this is a picture of the entrance area in the Ashoka University. If you ever happen to come by, I'm usually to be found somewhere over there. Talking about the future is anyway a difficult thing. As Paul Valery says, it changes. It's not like what it used to be. And these days, even the past can change. Forget about the future. The other problem is whenever you speak about the future, you're always looking backwards while rowing forwards, like rowing a boat. So you learn from past experience, but you have no idea if a rock could be, coming out. So this should always give you humility while trying to talk about predicting futures, because you can only rely upon past experiences, but importantly, your imagination, and even more importantly, planning regarding what is the worst thing that could be lying ahead. Things get a bit easier when you limit yourself. When you limit yourself to talking about health, health is a developmental goal, and science and technology for that purpose. Now, science again is a very broad word. It's knowledge and understanding of the natural and social world. Now, this is one of the reasons I went to Ashoka recently. Most of us think of science as only natural sciences. But really, when you think about impact and greater change, it's about change for whom? It's for human beings, right? And that's a social world. So, which means the artificial distinction of science and humanities is pretty much over. It is natural and social sciences, and research can be in any aspect of all of this. I have spent the most of my career as a lab researcher, sometimes a little bit on the field as a public health researcher. But as you go forward, you realize that when we talk of interdisciplinarity, we shouldn't be thinking of between computer science, mathematics, medicine. We should be talking about all fields of inquiry, particularly in health, which is an intersectional science. Now, technology, very obviously, is an application of science towards practical aims. Now, aims again for what? For society. And sustainable development, what does it really mean? It means about a continued progression, not something that stops. Then, you don't know what's going to start again, towards a future that you want. And you must realize there are multiple possible futures at any given point. And in mathematics, there's something called a Markov chain. You try to work backwards sometimes. You have to predict out which decisions are most likely to get you to the future that you want as part of a series. And of course, all of us know it's an SDG3 and this wheel has health in it. But what is the biggest change that's happening around us? One of the most obvious things is ever try showing a old film camera to a person who's 15, 20 years old. They will not recognize what film is. And this kind of a change is completely different from most of medicine, for example. I mean, I don't see too many patients anymore, but I'm very certain that novel from 1994 could probably treat most patients of now with only minor modifications. So, this digital transformation is occurring at a very fast pace, changing society, is yet to fully change health, but on the background of it, major changes are happening that will suddenly come together in the next couple of decades, and we need to be prepared. And this digital health is very, very different from the way people think. So you can think conventional health and use IT and telemedicine and mobile phones to deliver it. Or you can see there's a convergence of two types of revolutions: standard digital information communication technologies and another technology of genomics, which is breaking you down into digital codes. So the digital human, not from an ICT point of view, but from a fundamental biology point of view, and the convergence of these two revolutions is going to be the true digital health. And when you start thinking about a new version of health, in which you are reimagining healthcare, things like sequencing of children at birth could very much be part of it. It's technically doable. Should one do it? Is the question. And some of you who are interested in AI probably have already played with this thing called ChatGPT from OpenAI. I mean, it's been great fun. If you haven't, please make an account and do play. Any Gmail account allows you to log in. You will be blown away by the type of answers, but forget answers. I was recently playing with it and I've said, okay, tell me vaccinations for so many countries. Okay, tell me deaths. Now create a table. You're just speaking in text, just like natural speech, as you would to an assistant. And it's, creating fully formatted tables for you ready to go. But even more interestingly, Rob Morris, who runs a mental health service, he decided to use ChatGPT in dealing with people doing phone calls and trying to do texts to help manage their mental health. And of course, he had human supervision to keep it ethical. But very amazingly, what he found was response time dropped by 50%. Patient satisfaction increased. So, using ChatGPT, which is a pure AI, in a conversational mode, to people dialing in or texting in for basically having a discussion on mental health, and AI was receiving better ratings than a human being. Of course, he ended the experiment when he disclosed that AI was being used. Suddenly, satisfaction fell. Because, for a computer to say, I also feel for you, is meaningless. Computers don't feel. So much of what people expected was solidarity, support, which are human qualities. So, at one level, AI can do a lot. At the other level, what is the real expectation, sometimes why the placebo effect works in medicine, is because what people are expecting is human care. And you never should forget that. I mean, ultimately, patients come to get well. Whether they get well because only the medicine or because the doctor listened to them patiently and gave them a sense of confidence about their illness, it's all important. And in the end, most things are in your mind. Even your body is controlled by your mind, and people know that even things like meditation can have profound effects on physical symptoms. But let's move away from that. Let's talk about the 6 scientific trends and emerging technologies relevant to the future of health. These 6, to my mind, and I have edited them somewhat from the Nature paper I refer to over here, are big biomedicine. I'll explain all of them. Read, edit, and write genomes. P6 medicine that we'll spend some more time on. Typically, it's called P4, but for a reason that I think now, after the COVID pandemic, we realize the importance of public health orientation as well as psychosocial components. For example, children, elderly people, cut off from contact with other people, so many things we have realized. Regenerative medicine, immunotherapies, and brain computer interface. Of these, the most advanced are immunotherapies. You all hear about checkpoint inhibitors and CAR T cells and things like this. And so, what do I do today? I take the one that is most advanced and probably is the topic of a more qualified person than me. And we don't discuss that, but let's talk about the others briefly. So, big biomedicine is fundamentally about starting from the science, starting from the bricks, understanding the blueprint, and trying to see can we understand the genesis of health in that direction. Whether it be an atlas of cells, or an atlas of genes, or an atlas of proteins, or atlas of genes and proteins and something else in cancer, all these efforts are predicated that if you understand the building blocks and the blueprint, you will be able to make sense when something goes wrong in the building, right? In typical engineering, of course, this works. If you're given the blueprint and the building blocks and you can make changes in them, you'll understand. It's a bit harder, we'll come back to, but this is the basic idea. And massive global efforts are happening. And even in India, we are not running too far behind. We are behind in the sense that we are a LMIC, so the amount of money that's been dedicated to such research has been limited, but the technical capacity exists. Now there is an Indian Cancer Genome Atlas project, there is a IndiGenome project, there are multiple projects currently going on. Reading, editing, and writing genomes is also extremely exciting. We hear more about reading because you can sequence a person who comes in with a cancer or genetic disease and you can make sense of what's happening. You're starting to hear about editing, change one base in sickle cell disease, and put the same person's stem cell back into that person, and now the person is cured of sickle cell disease. Already 3 countries at least have done such work. There are multiple, well, not multiple, 2 published New England Journal papers showing how it can be done. And India is on course using its own patented gene editors to get into clinical trials in collaboration with AIMS. So there's an IGIB, my former institute, and AIMS collaboration, and the phase 1 in human should start within 3 years from now. So which means that technologically, these things are happening. You have to really navigate a lot of intellectual property. Even in reading genomes, interestingly, until some time ago, there was intellectual property. So many of you may have heard about the BRCA gene, right? It became famous when Angelina Jolie, because of the mutation she found, decided to get rid of breasts and uterus and ovaries. This gene and the mutation was known early in 2000s, but you couldn't test for it. Even if AIMS had the ability, knowing the primer sequences, AIMS could not have done the test easily because the mutation itself was patented. The American Supreme Court decided at that point, because such tests come from natural knowledge that exists in nature, was there to be read, and only the first person to read the book can't claim ownership of the book. So they came out with the judgment what already exists as a sequence in nature cannot be patented, which opens up this entire. And that's something that's very important. Very often you will hear about science as a way to generate wealth. It's important. At the same time, generating wealth as a process to become exclusionary and limit the benefits would be very, very antisocial in that sense. And when you talk about health for all, there's something to keep in mind. The most exciting thing, also the most frightening thing, are fully synthetic genomes. You will see the paper listed at the bottom over here. A complete synthesis of an E. coli from completely coded genomes, which basically means you can make completely synthetic bacteria. It's frightening. It's also amazing. This is where we are. Bacteria scale genomes can be synthesized. As you know, you only need DNA to bring back a full bacteria, right? So you can create synthetic organisms for better or worse biotechnology or health. Whether microbiomes and diabetes and introduction of synthetic organisms into your gut to create metabolites that you need. Perhaps B12 deficiencies will be sorted out by synthetic bacteria that can make B12 for you in your gut. Eventually, all B12, we talk about B12 coming from animal sources, but eventually, all B12 is made by bacteria. The reason we think as medical people that it comes from animal sources is because those animal guts are often rich in them, so they have high levels of B12. Then we eat the animal, we get the B12. But ultimately, the source of all B12 in nature is bacteria. And this is just the beginning, right? At one point, there were X number of vitamins, then it becomes X plus 1, then X plus 2. We are yet to discover everything. This one highlights the challenges ahead of us. On the top left, you will see two names everybody knows by now, right? Emmanuel Charpentier, Jennifer Doudna, CRISPR, gene editing, Nobel Prize, extremely well known. On the right side is a person who probably found something that's equally important in terms of where the field will go, Helen Hobbs. She gave a lecture in the Cell Press series. Some of you might have been lucky enough to attend it. So what she found was in a community of Afro-American people living in Texas. And for those of you who have some experience either by reading or visiting America, Afro-American person living on a Texas diet would not be expected to have low cholesterol. But she found those people with low cholesterol and looked what's different about them. Most of us focus on genetic variations leading to disease. But these are distributions. For every extreme distributions corresponding to what you call disease, there should be one on the other side corresponding to better health. In fact, recently at IGIB, we sequenced the genomes of 100 people who lived to over 100. So figuring out that's where we'll find them. And India is a great place for discovery. Suppose you want to find out a genetic variation that gives you great lungs and resistance to coal dust. Well, only in India can you find it, because only in India will miners still continue to be exposed to coal dust. Check 10,000 miners, if you can find a few after 20 years of mining, still have great lungs, you may be on to something interesting. In any case, she found a natural mutation in a gene called PCSK9. That mutation disrupted the gene. And if you are a pharmacology person, that's the best type. You can create antibodies, you can create drugs that block the effect of that gene, and within a few years, probably the fastest I've ever seen anything to go from genetic discovery to treatment, PCSK9 inhibitors, blockers have gone into therapy. And today, if you can't take a statin, that's your choice. But now comes a more complicated question. In a monkey, in a single dose given to the liver, you can create, already we are seeing 3 years of lasting reductions in cholesterol, probable reduction in cardiovascular risk in those models. At what point do you say, let's take human beings and give them low cardiac risk? And what point do you say, let's do this beyond cardiac risk? Everybody understands cardiac risk. So when I say this to the room, you will probably say, yeah, that sounds okayish. Everybody has heart disease risk some way or the other at some point. If we can lower it for them, it's a good idea. But we also know mutations in a German family that give super strength. We also know mutations that give eye color. We also know mutations that give skin color. Where does this slope end? Right? At what point would you say, no, this is not a risk? Difficult things. Being stronger is nice. Having a low cardiovascular risk is nice. Having a low cancer risk is nice. Elephants don't get cancer. Do you know that? They typically don't. The answer came, they have extra copies of the p53 gene. The more the number of cells you have, in theory, the likely it is that some cell will become cancerous. But yet elephants don't. That is always a surprise. And the extra copies of p53 seem to do it. So why don't we go around giving people extra copies of p53 now that we can? And perhaps the answer might still be okay, we stay to somatic editing, which means you can't pass it on to the next generation. But let's say we are convinced this is certainly a good thing. And I have the technology to also do germline, which means, very cost-effective interventions. Ek baar ki, now it runs through the families. What are the implications of that? Today we all say very clearly and with good scientific evidence, most caste, ethnicity, etc. are socio-political constructs. They have no biological basis. But once you start tampering with genes, would that statement still be accurate? What would be the meaning of equality in society once you are tampering with the fundamentals? Many interesting issues to come out. Anyway, we'll come back to that a little bit later. Let's move to regenerative medicine. Again, a very famous paper. If you haven't read it, you should look. So mice are genetically identical to each other. So it's easy to create these hybrids where you can connect the circulation of a young one to the circulation of an old one. They're genetically identical, so there's no risk of reactions. And what you find is the old one started getting younger. just by mixing the two circulations. A lot of new work will come. Some of it is not yet published, but people will show it as exosomes coming out of a variety of stem cells that are driving some of these changes. Exosomes are little packets of information that a cell sends out. They can fuse with other cells, and people are now able to recapitulate some of these effects by simply taking exosomes of stem cells and re-injecting them, and a bunch of other factors too. But actual cognitive decline started getting reversed. One of the hardest things to do. So the mice got smarter. I mean, it's hard to know the mouse is smarter, except to put them in a maze and see the amount of time it takes them to find the way out. So clearly, that would have been the final frontier, right? I mean, almost all of us know, given sufficient time, we will figure out how to replace limbs. Given sufficient time, we will also figure out how to replace organs, such as heart, which are mechanical. Things that are more than mechanical will be a little bit harder, but we will eventually get to liver and pancreas as well. And of course, excretory organs are already partially mimicked. But this brain part is what's been worrying a lot of billionaires. The biggest investments in America right now are coming in two very interesting areas. The first is this, aging, dementia. The other one, very interestingly, that again I will not talk about today, but it's of great interest, is psychedelics. So people are realizing that perhaps there is some basis towards use of compounds that alter brain function in changing things like depression, creativity, things like this. And of course, we come from a country with a very rich tradition of the use of psychedelic compounds in moderation in specified ways. And our current attitude towards these drugs comes from a very Western view of everything being illegal. So that's a very interesting area of research. Big institutes are being founded in the West. I claim to have zero experience on the subject, and we'll see how this field goes. That's an emerging area, but not for today. But having mentioned that, the other frontier is brain-computer interface. Don't know how many of you saw this, but now you can think about an action, and a computer can understand the motor function you're thinking of and carry it out. That's easy. There is a clear motor cortex where particular patterns of activation occur for a particular action that you want to carry out. Given that a computer is recording EEG from those areas, and you're thinking of carrying out those functions, eventually, by machine learning, the computer will learn what you mean. That was always possible. And brain-controlled commands for physical motions of fire or something like this have been around for a while. Now you can do speech. That's very fine motor. That's not coarse motor function. Now you can think about speaking a particular sentence, and a computer can figure out what you're trying to say and say it for you. Absolutely path changing in locked-in patients who have lost these functions. Path changing in people who have had major strokes. And again, you can see the relevant papers listed to the site. Other very important area is the science of modulating behavior. At one deep level, the neuroscience of pleasure is a very nice blog. Do look into it. There is a very famous patient called patient B19 from a Skinner box type of an experiment where you give carrot stick type stimuli to people to change behavior. Once upon a time, when people did not think of sexual orientations as normal, it was decided to see if they could convert somebody who was male but had homosexual orientations to a hetero orientation by experimenting with electrodes and pushing the brain into sensing pleasure. They had partial success. Today, we are moving to the point of subliminal cues and changing people's behavior while on social media. This is being again thought of for good. So you can detect potential depression, suicidal ideation, and nudge people towards the right behavior. But this business of nudging again is a complicated one. So we have a wonderful Center for Social Behavioral Change at Ashoka University that looks at nudges, particularly digital nudges. It in fact worked with Niti Aayog during the vaccination program. What's the point of vaccines if you can't nudge people into getting the vaccine into their arms. So there are good nudges, but very clearly there will be bad nudges. And in fact, the even word good and bad have a matter of judgment ascribed to them. So complicated things. So all of them are dual use technologies. You can use them in the way you see fit, and what is one person's good could be another person's bad. History is great evidence. I won't get into the morality of it. But this will automatically raise the question, when you imagine the health of tomorrow, who decides what is good? There is no right answer. The rightest possible answer amongst many possible answers is whatever is decided by the largest number of people thinking together. The smaller the number of group making the decisions for everyone, the more wrong it is. The larger the participation, the more right it is. Will it be constant across generations and ages? Of course not. I mean, people who lived a few hundred years before us were not any stupider or any less moral-minded or worse people than us. They were just different. So will be the people who come after us. The best you can do is to not assume that people who control healthcare, the doctors, or people who control science, the scientists, are by themselves capable of taking decisions that impact all of society. It would be even more foolish to pass on such responsibility and roles to people simply based on the chairs they occupy. Chairs are even more temporary. At least profession runs for a while. It is simply about empower the public, empower the policymakers in engaging with the public on such debates, and then seeing what comes out of it. And making sure that people with the maximum skin in the game, with the maximal conflicts, don't automatically get to determine where the debate is going. But there is no more that one can do. So, these 4 words: enrich, educate, engage, empower, ultimately enable. And this is a great example. I wonder if most of you, I'm sure many of you recognize Dr. Hay, right? The first CRISPR babies. Look at his justifications. His justifications were he wanted to make sure that children born to a mother with active HIV are resistant to HIV by mimicking a mutation that was known in nature and has been shown to completely cure HIV. So people with HIV that have received bone marrow transplants from donors containing these mutations will no longer have HIV after they're done, because the virus simply can't enter the cell. So he was trying to engineer those mutations into babies being born to parents and mothers that had HIV. So you can see in his mind, he had a justification. You could even argue he had consent to some degree. But where is he currently? He's in jail. Reason it is not done as per the wider understanding of the public. There was no attempt to truly inform and educate before getting consent. Remember, it is not consent, it is informed consent. And informed is a very, very complex word. Informed regarding what? Informed regarding the technology you are be using to do it and the safety of the technology? No. Informed regarding the implications, what is happening. Who all are to be informed? Only the patient, or was the ethical committee fully informed? So again, those of you who will be getting into emerging areas of technology, keep this in mind. So I'll come to the part of the talk that I perhaps feel most comfortable with. The others I think are very interesting. I'm engaged, I'm learning. This part, P6 medicine, originally called P4 medicine, deals with data, artificial intelligence, and healthcare. Many of us think that the quantum leaps in healthcare technology are the devices, only to a small degree. The real quantum leaps, and that was said very nicely in this nice paper in the New England Journal, a glimpse of the next 100 years in medicine, from the inferences drawn from the data from those devices. But how many doctors are trained to work with data? Most of us won't recognize the model of it bit us, a complex model. And the problem with AI is it's not always explainable. So which basically means that as you use more and more information coming from more and more devices, informing about the state of health, you will end up with analytical algorithmic formulas that will be useful for clinical purposes, demonstrated in trials, re-demonstrated in trials in India, re-demonstrated for the skeptics, but still not summable in a language that doctors understand or patients understand. It's simply not possible. It's not about let's train doctors in AI and mathematics and they'll be able to do it. Even the AI person cannot summarize it in a language that anybody can understand, because there is no language basis of the understanding. I'm going to come to this. And which basically means that we will be at a point where all these devices will be creating a twin of you in a digital world that is actionable by algorithms, and the results of that probably map back to the physical world, but nobody understands what is really happening. So, once upon a time, and this is a picture of the Apollo 13 mock-up in NASA, when the first physico-digital twin was created. And this really turned out to be very, very useful, because when the oxygen cylinder exploded on the Apollo 13 mission, and they called back saying, Houston, we have a problem, you had the ability to diagnose and solve the problem of a failing physical asset 200,000 miles away by simulating, because you had those mock-ups. Now, of course, it was not a true twin, because a true twin must be updated from real-time data, right? I mean, here they only had few communications coming by radio every some time, then they would make some adjustment and then they would simulate again. But you get the idea. A baby could be sequenced at birth. Sequencing, of course, is not enough, so you could do many other omics. You could put devices from childhood. You could do many neuromonitoring, behavior assessments. You could pretty much create a in silico progression of a baby's growing up. And you could, in theory, use it to learn. In fact, given the complexity, who else could be trusted with managing so much data? Certainly not the family doctor, certainly not the parents, and certainly not the baby. So who else except an AI, which is continuously updated regarding what to do with this data, would keep track of such a person? And at a very, very small level, this is starting to come. So now if you buy a Porsche, and I hope some of you will, the Porsche digital twin can predict when your car will need service. As of now, the only digital twin is for the suspension. So when you go over a Delhi ka speed breaker, the Porsche digital twin will know it went over a Delhi ka speed breaker, and the service now moves 10 minutes earlier. The same technology has been there for jet engines. So for example, to service a jet engine of a Dreamliner is expensive business. Every day the Dreamliner does not fly costs you money. But different engines are different from the day they were made. Then some engines may fly through a sandstorm in Arabia and some may not. So a digital twin of a jet engine knows the environment, the particles, the flight histories, the locations, and gives you servicing guidelines or recommendations based on that. Same thing now for a Porsche servicing. If you're going to pay a few crores for a car, you want to know when to service it in time and not unnecessarily keep sending every 3 months. And most importantly, simply because people will pay for such things. But when it comes to healthcare, we are still very, very far away. Biological systems are clearly very, very complex. But is there any part of medicine that is close enough for this to be actually working? Interestingly, cardiology. So, and that too only one small problem within cardiology. So the heart is a electromechanical organ. We understand electro to some degree, we understand mechanical to some degree. So people with heart failure, dilated hearts, have electromechanical problems. The impulse, the QRS complex is not reaching on time, different parts are getting activated at different times. You want to do a resynchronization. You want to see the optimum distances between atria and ventricle beating. You can put in complex pacemakers with these capabilities. These pacemakers can give you back all the information that you need to build a twin of the heart. And then you do something like this. You plan an entire cardiac resynchronization therapy in silico. You kill the patient in silico if it goes wrong. And after you divide multiple strategies and one that seems to work best in silico, then you do it for humans. So this kind of work is already starting to happen in Germany, already being used. So you're getting to the point of a simple electromechanical organ with invasive pacemakers placed so you can get data, twins being created, and those twins being used to simulate interventions, sometimes leading to death of your in silico twin, which makes no difference to you in real life, and then it coming back as an optimized therapy for you. It will happen in other things. It will happen in cancer, where primary cultures will be done of your tumor cells. It will perhaps even happen in continuous sequencing from blood of people with cancer, looking at resurgence, looking at new mutations, and planning of entire cancer therapies. It will happen in drug discoveries. It will happen in many things. But this is just the beginning. And of course, when you collect these massive amounts of data, Dilbert is very rarely very far away from contemporary topics. So this is again a Dilbert cartoon. And you can see that, the boss wants to know everything about everybody from the watch that they wear. And because you care about health, yeah, we'll go with that. So yeah, you have to be careful about, what exactly you accept when you allow a digital twin to be made. So this is the real fundamental of health tech. They may be partners, they may be halves, but clearly health is the better half. There must be a purpose. The purpose is easy to state. New technology is not going to be the only way there, but to deny the need for technology is also wrong. To say we can manage a graying world with current technologies is simply unrealistic. The number of people, young people, able to provide manual assistance will fall. Sooner or later, management of elderly people would either come from enabling systems that allow them to live independently, or will come from robotics. There is no other way. In countries like Taiwan, where the average age has crossed 50, 55, I think, is roughly the average age of Taiwan, they are thinking about these things very, very seriously. Regenerative medicine will help extend the working physical things, but at some point you're going to have people who are alive but need assistance. So our commission, the Governing Health Futures 2030, that I co-chaired in 2019, looked at some of these topics. It was a reasonably diverse group of people drawn from all over the world. And I'm not going to speak much except that you can find the recommendations that we put in this particular issue of the Lancet. But the basic point that we set is the digital health ecosystem is fundamentally grounded in users and their data. It's obvious, but you need to state some of these things out as a matter of fact. Every nation will need a very clear articulation of its vision on how such data will be generated and used. We are lucky that India has a very clear national digital health mission. It has digital health authority. There is a belief of the concept of digital public goods. If any of you use UPI, that's a digital public good. You use Aadhaar, it's a digital public good. There are only 4 pillars that a system needs. Everybody needs an ID. Every transaction and provider needs to be known. Everybody should have insurance. And transaction should be able to occur on a common platform. Once you have all 4 of these pillars, which in India everything is in place, you are very, very well placed for the next step. Using a digitally transformed system, you can use data flow for good. And you can have different layers for different people. And the biggest challenge everybody discusses is, the privacy rights and what should be. And today we speak about consent-based architectures. Again, I would tell you, it's a wrong word. Consent is not informed consent, and none of us really knows enough to provide full information. What is in fact, you would find that you give consent every day on your phone to a variety of things. Every time you want to use a new interesting feature of your phone, you click OK. The bigger the company, the more able it is to get you to click OK. In fact, the smaller company, which is local, will not be able to provide you the incentive to say OK. So a consent-based architecture actually skews the field. It sounds very nice and ethical and honest. It completely skews the field towards established players, most of whom are international. So what is more important is a concept of solidarity. Health of an individual and health of a community run together. We saw that in the pandemic. The idea should be how to make data more easily usable for multiple people for the right use case scenario and what it cannot be used for irrespective of consent, and to protect people from the choices even after they have given consent by limiting the use cases, the applications, and the consequences of misuse. That is where states can come in, as opposed to doing the Western way of GDPR, in which consent becomes the dominant thing. In fact, you would say almost all the data in India will go waste. Nobody can even track the person back to get any consent. So India needs to think very differently. And that is one of the things that I meant. You must be thinking of the outcome that you want, not just of individual little bits and pieces of the process. And of course, you're going to have to deal with this challenge. What if all the data is wrong? And we know that, pandemic or many other things, heterogeneity between data from states, huge number of things. Data can sometimes be misleading, and horoscopes is not really the way to go. So I'm going to start winding up by talking about some of the successes and failures. Some of you may have heard about the game of Jeopardy. A typical question could be, the name of this hat is elementary, my dear contestant. Now, to those of you who like Sherlock Holmes, elementary is the trigger word, right? Elementary, my dear Watson. To those of you who love Sherlock Holmes even more than this much, might remember the deer stalker hat that he wears and might come out with the answer, deer stalker. Now, if I were to ask Google, what is the name of the hat Sherlock Holmes wears? It'll give me the answer in a millisecond. But that's not really the difficult part. The difficult part is figuring out the question. So when IBM built the Watson program to fight Jeopardy, this is what their architecture looked like. Most of the AIs they built were to break down the question. So multiple AIs broke the question into pieces that allowed the Watson program to figure out what the question was. Finding the answer was the most trivial part. So they actually came out with the same question would give you multiple question answer pairs with confidence in the question and the confidence in the answer to that question. And the best pair would give you the final answer. So it turns out that this used to be the challenge at that time. Today with ChatGPT, as I showed you, figuring out what you are saying is getting easier and easier for computers with more and more access to data. It's the data that's making the difference. Every time you interact online, every time you click that button saying mark the squares with a cycle or a red light, you are training them. And this, of course, was the result that Watson beat the two winningest ever human players. Then, of course, IBM got emboldened to say, let's cure cancer. That became Watson for oncology. And that we all know didn't quite succeed. Why? Jeopardy has clear answers for all questions. Jeopardy answers only need existing data. But in real medicine, there may be no right answers to the same question in different contexts. In fact, all answers may be wrong in a given thing. So these are the type of realities of medicine. And for example, Google can tell the gender from this. I know that none of the doctors sitting in this room, well, all of you can tell the gender of a person before you look into their eyes. But after you've looked into the eyes and taken the snapshot, you can't do anything in telling gender. But Google DeepMind can. How can Google DeepMind tell the gender, the age, the current smoking status from a photograph of the retina? We don't know. ADAC is pretty good. Try it out. It's available freely. For common symptoms, put them in, see what it comes up with. It's a very good symptom cross-checker with differential diagnosis generator. Protein folding, massive problem. DeepMind originally started with playing games. Today can fold proteins. Ultimately, what is a game? A game is something with an outcome. If you change the target to finding the right structure as a winning, the AI learns. A new class of antibiotics was recently discovered, helicin. So I think we are looking at some very exciting times ahead. But it's also good to remember one important failure before I end. Respect for autonomy, privacy, and ethics are not based on algorithms. Unbiased collection of biased data does not eliminate bias. Right? All you can do is be unbiased in your collection. You can't get rid of the bias that's in the data. If women's heart attacks don't get recognized because they're atypical, right? What is the meaning of this? That's 50% of humanity. So an atypical heart attack for a woman is not a very satisfactory description. And if based on typical things that got picked up easier, the entire database is skewed, well, the AI will learn exactly the same skew, no? And we had very interesting experiences during the pandemic where we realized that AIs that were good at classifying COVID versus non-COVID X-rays were not looking at the X-ray. They were reading the name of the hospital. Because in the training data, all the COVID films came from one place and all the non-COVID from another. All they had to know to figure out where it's COVID or not is read the name of the hospital. All kinds of interesting things happen. But this is perhaps the most frightening one. It's a paper by Obermeyer in 2019. In America, an algorithm is used by insurance companies to find out those people who need additional care in outpatient to prevent admission. They say the only person who really cares about your health, even more than you yourself and your family, is the one who pays for it. So the insurance companies want to keep people, well, insurance companies when they intend to pay. When they don't intend to pay, they don't care. But insurance companies want to give you additional care as an outpatient to prevent big cost later as an inpatient. So these are black patients, these are white patients. That's the score coming out of the algorithm, and that's the number of active conditions they have. Why should black people have more active conditions to get the same score from the algorithm? Algorithms don't care about skin color. No insane programmer could have introduced bias by saying discriminate against the blacks. I assure you, you do this by caste or by poverty in India, or anything, you'll get the same thing. Why? How do you know someone is sick? You know someone is sick when they seek health care. Are people equally sick before they seek health care? No, they aren't. Richer people can go to a doctor for a cold. A really poor person might wait for a mask to be hanging out of the head before they go see someone. If you're going to figure out sickness from use of healthcare, you got a fundamental bias the day you started. But an AI does not know that. An AI assumes a society is humane and real and nice, and people who need healthcare get it. Only proper human supervision would allow you to get over these things. And this is something very, very critical. And we must be very careful about how we use AI going forward. It has a tremendous potential for good, but potential for very, very wrong conclusions if you allow it to be misused. So, to end, when you talk about the emerging technologies and the frontiers of healthcare, will it succeed technically is a small question. It will eventually. Those are fixable things. The bigger questions are whether it will let future generations flourish. Will it increase equity or not increase inequity are other things. And in the end, all of you must participate in the design of these things from the beginning. Young people in particular are super important because the concerns of old people when they speak of health are different. At a particular age, cancer might be the most concerning. At my age, CVD might be the most concerning, or diabetes might be the most concerning. What's most concerning to a young person? Wellness. That could include mental wellness. In fact, mental wellness could be the foundation to physical wellness. When we ran something, we came across things that we actually did not think in the beginning. Sexual health was very important to young people. Identity was very interesting to young people. To them, the digital world gave a source of identity. They could be who they wanted to be. And I must confess, I'd never fully saw it coming. Of course, when I look back, I can see how did I not see it coming? But the point is what's important to young people, what health means to different people, what wellness means to different people, involves co-involvement of younger people in the design of these systems. Universal healthcare should mean access to each of these, including mental health, and access to the right information. And in the end, I'll only repeat the law of Roy Amara law. We always tend to overestimate the effect of technology in the short term. So, all of us thinking AI will solve India's problems of, poor accessibility to healthcare in the villages. In the short term, we are overestimating it. Not much will occur. But almost none of us can ever fully imagine how much it will change the entire vision and the face of health in time to come. Thank you. Happy to take any questions, whatever is there.
They are pretty clear.
All right, fantastic. Please.
Healthcare data leak, like how would it affect us normal people?
So healthcare data, let's take an example of some practical things that I've worked. A is the use of healthcare data to train systems to mimic what humans do, right? I mean, so example of that would be, I have a shortage of radiologists in this country. I want to be able to find strokes very fast. It's easy to install a CT scanner. It is easy to find a technician to run it. It's difficult to find a radiologist to read the thing in the middle of the night. I could take health data and images from all patients with stroke. I could extract that and I could, use an AI tool to predict stroke. It's already been done. It's in fact a company in India called Cure.ai that has led some of this kind of work globally. And today you can get an automatic read for strokes. Similarly, they have done work for tuberculosis. Similarly, other things. But that's really a very, very, low hanging kind of a thing. A more ambitious application would be something different. That could easily be something, for example, trying to do a virtual consult. Today in Stanford, if you walk in, you are a very interesting rare case, and nobody knows what's happening with you or what to do for you. They can call in a virtual consult from a division of virtual medicine run by a person originally from Baroda Medical College called Nigam Shah. He is now the Chief Information Officer of Stanford Med. He will use all data available in Stanford records to find the closest matching patient. They will find out, because that patient has the full records are available, what the final diagnosis was, what they responded to. In multiple cases already, these kinds of things have made a difference. So at the extreme example, you could take the entire data set and do a virtual consult. So we are planning of doing something like that with Max hospitals, which actually have electronic medical record data for at least 15 years now. And they are creating a data lake, which is all interconnected. So these would be the two kinds of extremes. One is a very specific problem for which you extract the data that you want. In the other one, you don't extract anything. You let data be the way it is. You ask a deeper question.
Thank you for a very interesting talk. Even for a computational biologist, this opened up completely new scintillating ideas. So, as somebody who works with data, my only question is, how to make this kind of data, of course, anonymized data, how to make it more available to people who are interested in working with it, who are interested in mining it? Where are our biobanks? Where to go with
Great question. So we have been thinking in India about de-identified data sets. My personal opinion, that's the wrong direction. You really cannot de-identify some types of data. Not many of us are aware, but Indians are both the genetically most diverse and the most inbred people in this world. If you take the entire population, we are very diverse, right? Imagine you want to ask I'm going to digress slightly to answer your question better. Is that okay? Imagine you want to ask him a question, how related are your mother and father? What you can do is plot on the y-axis frequency, on the x-axis the length of the segment identical between parents. you can imagine the more related they are, the longer the segment that will be identical. So let's imagine a typical person in America is roughly at this level. An Ashkenazi Jew is somewhere around here, or a Finn. Many Indian communities, including mine, hit the roof. Because for almost a millennia, you keep marrying within the same narrow pool of people again and again, which also means that our genomes inform of communities. For many communities, just a look at the genome at IGIB can inform regarding the last name, pretty much. So you find something. Well, any link to that community now becomes obvious. So de-identified datasets released cannot always be called to be truly private. And number two, whose privacy? Your genome is shared by your offspring, your cousins, your brothers, and all these people who all will give consent. So what I prefer, which is in my opinion the right model, are privacy preserving architectures where nobody gets to download the data. So everything is federated. Your algorithm can go in, get a parameter out, but can't actually download the data. Can't download anything about the person except what the parameter is allowed. So whether you call it federated learning, whether you call it swarm learning, these things have been shown to work. Something interesting Ashoka is doing, very interesting work. You continuously add and subtract noise. With every piece of data that you're adding, you also add some noise. And towards the end of whatever thing you're doing, you either subtract or multiply or remove it. So you're simultaneously noising and denoising the data so that there is no reality except in the final conclusion. So these privacy preserving methods of using data are superior to de-identified datasets. Let's see where it goes. Because de-identified datasets, the direction we are going, it will almost certainly be challenged in court for the reasons I'm saying. Because de-identification does not always mean give me the name of the person. Let's say I have a list from the government website of these are people I don't want to insure. Right? I don't know their names, but I have some information. Every time a new person comes in, I ask a question: what is the probability of this new person belonging to that data set of the people I don't want to insure? The computer can give me a percentage, and I set a threshold: 90% probability I'm not going to insure them. I have created discrimination without knowing the exact identity of anyone. So again, and this is something that I learned when I started speaking to economists who don't ask about de-identification, they ask about the purpose of de-identification. They ask about the economic value of anonymity. So it's very interesting. I mean, so more discussion between humanities and science. That is a long answer, but hopefully that makes sense. All right. Thank you all so much. Pleasure to be here. Yes, please.
Thank you, sir. This is very interesting talk. First, I need to understand. Suppose the patient have diabetes, CKD, and other disease also. How can we distinguish that this patient has this disease or the treatment is needed?
So there are two ways. In America, they do it by insurance codes. So what happens is to collect your money from the insurer, you have to check all these little things. And because collecting money is usually important to all people, they are very good about checking the boxes. The other part is about reading the notes of the doctor. So if the doctor has not checked the boxes, they'll still have a note somewhere. So those are in the category of natural language processing. It becomes harder if your notes are pieces of paper that are scanned, but it's relatively easy if they start with digital text. Because, and I'll tell you, the biggest problem comes from if you use pieces of paper that are scanned, symbols, diabetes, cross. You don't read the cross, you think the diabetes might be a yes. So many small such things, but yeah, either NLP of notes or from records given for reimbursement purposes. And there's a new move by which patients will have access to their own medical records in America and will have the ability to log in and suggest corrections and updation. So this year onwards in America, patients will have the right to access their own medical records.
always a pleasure to hear you, Anurag, and so he's beautifully highlighted the use of technology and how we are. I mean, I'm sure. I mean, technology is there. It's going to be in everything that we do, and in the basic sciences, clinical sciences, in everything, the use of technology is increasing, and we are bound to use it. However, many of us may not like it, or many of the old people with old school thought may not like it. But yes, it is there, and it has to be used. Coming to the question, the interesting question that Sonika asked about the data mining or availability of data. That's a one big issue in our country, particularly where we do not have any EMRs. That is the major issue, and that makes it really difficult for clinicians, or even who want to have see the data from the large surveys. Government does the large surveys, National Family Health Survey, the National Nutrition Survey, and all those things. But how do we get that? How does one blast that data set and do the analysis like the Enhance does it, the Korea Enhance does it, and several other large countries, and the large data sets are there, and which are going on longitudinally for over a period of time. So you get the data as back as 2 decades back, and now what is happening. Enhance is a very beautiful example of that. They have so many series, and one really gets that how things are happening, how new whatever was considered not significant initially has now become significant. So, and new diagnostic modalities or newer markers keep on adding from that. So that is what I think is the importance of technology. And the bottom line is that yes, the use of AI is there in everything, but it needs to be monitored by a human being. What you put in is what you will get. So I think thank you very much for the beautiful lecture and igniting everybody's minds regarding the use this topic. And thank you everyone for being here. Thank you.
Thank you.